Okay, 137.3, the exercises. We'll start with problem number one. Certainly, I'm going to outline what we've done in the past. We've used certainly the rational root theorem in an attempt to factor the problem. My suspicion is that you could list the rational roots out pretty quickly. I should say the candidate rational roots out pretty quickly and start testing them. I will say that testing can be rather tedious. I don't mind using a calculator. And what I would find is, if you did test them out, I'd probably be the easiest one to test out. And I'll go through this step by step. I think f of minus 2 would probably be the first success you hit. Like you try 1, minus 1, 2, minus 2, you'd hit that. All right? And then you'd probably stumble on the 4. That's where I'd probably stop. And what I mean by that, that's where I'd probably just simply say I'm going to long divide and get a quadratic out of it. So let me point out what I mean by that. I would look at this thing and say, oh, gee, x plus 2 must be a factor, and x minus 4 must be a factor. That is, if f minus 2 is 0 and f of 4 is 0, that's got to be a factor. So then I would look at x squared minus 2x minus 8, and I would divide it into that. And that's what I did over here. Then you get this quadratic over here. And quadratics are easier to deal with, and that's the whole point of doing it. Looking at that quadratic, what do you get? It factors. Again, we're looking at this quadratic over here. Looks like 6 and 8. And it looks like plus 8 minus 6. So I found the additional 2 roots there. And what those additional 2 roots would be? 6 would be a root because it makes one of those factors 0, and minus 8. Now, using a rational root theorem, I don't think you'd get to 6 or minus 8. But I think minus 2 and 4 are not outrageous, right? So this is the way it factors over here. And you get the 4 roots. And the 4 roots are relatively easy to write down now. So the point of this section over here is doing that and getting those 4 roots, all right? And if that's the technique you took, that's a great technique to take. Looking at a picture of it, we've done many of these before. Minus 8 is one of the roots. Minus 2 is a root. 4 is a root, and 6 is a root. And again, it's a 4th degree polynomial. We're expecting to see behavior like this. All right, so this section over here was about Euler's method. And so in Euler's method, you're writing the equation down. This reminds me of the quadratic formula. To me, it's more work, though. Right? To me, it's a lot more work. All right? So looking at it, the coefficient on the 4th degree term is 1. It's a proper form. And then the a is minus 60. The b is 80. And the c is 384. All right? And then I write down this cubic form, which is t cubed. A divided by 2. I'll write that down for you. A divided by 2, t squared. A squared minus 4c over 16t, and then you get this over here. Now, if you do that, again, to me, it's way more work than I originally did. To me, it is anyway. You get this over here. Let's just go through that. When you take a and divide it by 2, you get minus 30. Let me write the a squared down. I think that's work. The a squared would be 60 squared, and then minus 4 times c. Well, 4 times c is 384, right? Again, for me, this is way more work. Over 16, you divide through, you should get 129. All right? And again, if you're not getting these numbers, let me know. Then the b squared over 64, you should get minus 100. All right? And then you're looking at this cubic form, and you want to get a solution to that. And again, to me, looking at it, I'm still using a rational root theorem. All right, I notice that t equals 1 is a solution to the problem. And why is that? You would get 1, whoops, sorry about that. You would get 1 minus 30 plus 129 minus 100. And if you add that together, you would get 0, all right? And then what I do is I depress the cubic by doing a long division or equating coefficients, and I get a quadratic, and then this quadratic is easily factorable. All right, so I'm getting 3 t's now. For the t's, I'm getting 1 25, and 4. And to me, I really think I've done way more work than me just using a rational root theorem on the original problem. I'm still not there yet, all right? So then what do you do? Again, we're using this Euler's method. Well, you put this down. Again, we're looking at this. Plus or minus 1, plus or minus root of 1, plus or minus root of 25, plus or minus root of 4. All right, to me, it's just a lot of work. We'll get the same answers, by the way. Minus 8, 6, minus 2, and 4. All right, to me, a lot of work, all right, to get that. By the way, you're really not done because you can make a mistake somewhere. Take the wrong combinations, whatever. But you go back over here, sorry about that, and check it. Check it in the original. Now, granted, we did it already. How do we do it? We went in for the kill on the rational root theorem. It's probably the easiest technique you come up with. However, I'm not trying to discount what Euler did. It's an important numerical technique. Looking at it, get through it, but I'm always going to start with the easy part first, then I'll go to the more difficult method later. Okay? Thank you.